and we'll look at some of the characteristics of rational functions like x and y intercepts, horizontal and vertical asymptotes, intervals that are positive or negative versus increasing and decreasing. So here are just some examples of a rational function. It says here that a rational function is a function in this form here. Really just means that we've got a numerator and a denominator. Ratio is really what we're referring to. And here are some examples of rational functions. Now, one thing to really keep in mind is that when we have a denominator and an x in it, we do have to remember that x is, or the denominator cannot equal to 0, and that's really a huge theme in this entire unit. Whatever value makes the denominator 0 is called a restriction, and we do have to state it. So in the first case, x cannot equal to 3/2 or 1.5. In the second example, x cannot equal to 0.5. And in the third example, x cannot equal to two values, 0 or 2. And you can solve that by setting the denominator to 0 and then figuring out what x could be. The first example here is called reciprocal of a linear. You can imagine this function here could have been a linear function, y is equal to 2x minus 3. And if we reciprocate it or make it 1 over that, we'll get this. So this is called reciprocal of a linear, and that's actually what we're going to be focusing on in this lesson. The second example is a linear over linear. We've got x in the numerator to the degree 1 and x in the denominator as well. And then the third one is, again, a constant, not 1 but 3. It doesn't change things much though, because we've got a quadratic in the denominator, and this is called reciprocal of a quadratic. So let's take a look at the reciprocal of a linear function. So a linear function is y is equal to x, and then its reciprocal would be 1 over x. That's really what reciprocal means. If we go ahead and sketch this, I use Desmos to get this, or GeoGebra. These are the two graphs that you get. The blue is the line, y is equal to x, and the red is its reciprocal, 1 over x. If you want to pause this video, you can try and find 3 connections or trends between the two graphs, so between the blue and the red. And here are some hints. You can look at intervals of increase and decrease, and behavior, as well as X-intercepts. All right, so if you've thought it out, maybe we can start off by trying to look at that both graphs are in the same quadrants over the same intervals. So to the left of the y-axis, both graphs are below the x-axis, and to the right of the x-axis, or to the right of the y-axis, they're above the x-axis. So they're kind of in the same quadrants. And we can kind of make sense of that because the functions are nothing more than reciprocals of each other. So that just means that when we find a reciprocal, the sign, positive or negative, doesn't change. Only the numerator and the denominator switch their positions. We make it 1 over whatever the original numerator was. So the sign doesn't change, which means that if the original function is positive, or in this example, the line is above the x-axis, that means to be positive. Well, that means its reciprocal will still be positive because we're just reciprocating it. We're not changing the sign. And then same goes for when the blue function or the linear function is negative. When we reciprocate the function and make it 1 over x, we don't make it all of a sudden positive. It stays negative. The other thing that you should notice is a graphical characteristic that the reciprocal function has when the zeros of the original function correspond to. So the original function, the blue function, has zeros, or x-intercepts, just one, at x is equal to 0, so right where my pointer is. When I reciprocate that function, so instead of x, we end up making it 1 over x, you would notice that that becomes a restriction. You should notice, because now x is in the denominator, and in math, the denominator is not allowed to be 0. So the x-intercepts of the original function is x is equal to 0. When we find a reciprocal, again, the numerator and a denominator switch, and now the x is equal to 0 becomes a restriction. X actually cannot equal to 0. And graphically, this restriction is called a vertical asymptote. So there it is. We've drawn it with a dashed vertical line. And an asymptote is nothing more than an imaginary line that the function doesn't touch, but it gets very close to. Lastly, explain why the reciprocal function is decreasing while the original is increasing. You can tell that the original function is always going up, so it's always increasing. The reciprocal, 1 over x, is actually the opposite, always decreasing. It's going down as I go from left to right. Even the second piece, I'm going from left to right, and it's going downward. So why is that? Well, as x increases in the original function, when I plug that same x value in the reciprocal, it'll start to decrease. For example, let's set x is equal to 2 and 4, and then we can find the corresponding y values. So in the original function, when x is 2, y is also 2. In the reciprocal function, when x is 2, y is 1 over 2. If I make x equal to 4, in the original function, y is also 4. In the reciprocal function, y is 1/4 because it's 1 over that. So the original function f of x is increasing. In the reciprocal function, I'm going from 1/2 to 1/4. It's really decreasing. Asymptotes. So let's talk about asymptotes. These are imaginary lines that a function approaches but never touches. The reciprocal function 1 over x has two asymptotes, a vertical asymptote and also a horizontal asymptote along the y-axis. So steps to finding these two asymptotes, and they're crucial. The first one is vertical asymptote. Remember, vertical asymptote is the synonymous to a restriction from the denominator of a rational function. So to find the vertical asymptote, you always do the same thing. Set the denominator to 0 and find x. These are, again, your restrictions as well. To find the horizontal asymptote, there's a longer way. I will show you a shortcut because we don't really need to know the longer way for now. I'm only showing it to you just because it's nice to know, but the shortcut is really nice to know, so you'll learn the shortcut soon. So to find the horizontal asymptote, the first thing we're going to do is we're going to divide each term by the highest degree of x. Then we're going to simplify, set x is equal to positive or negative infinity. We don't have to do both because really a horizontal asymptote is really concerned with x approaching infinity. On this graph, the highest x goes is 5, but you can imagine it goes to infinity. So when x approaches infinity, we want to see what happens to the function or y value. And also when x approaches negative infinity. So the horizontal asymptote is really concerned with these two ends, the left end, negative infinity, and the right end, which is equivalent to x is equal to positive infinity. And then we simplify and figure out what the y value is, and that is a horizontal asymptote. So if I have this function here, 1 over x, and I want to find the horizontal asymptote based on the steps I just talked about, first thing will be to divide each term by the highest degree of x. So the highest degree of x is 1, so that means that we're going to divide by x to the exponent 1. The highest degree of x is x to the exponent 1, so everything gets divided by x. And in this case, it's just 1 over x will end up being the 1 in the numerator will get divided by x, and the denominator, x, will get divided by x. And then we simplify. And what happens when we simplify? Well, the denominator, x over x, just becomes 1. The numerator stays 1 over x. Now we're going to set x to either positive or negative infinity. We don't have to set it to both. I will, just in this case. Let's go ahead and see what that approaches. So I can either end up with 1 over infinity divided by 1, or 1 over negative infinity over 1. Now in math, every time we have, or we divide by infinity, remember infinity is just a really, really big number. So when it's 1 divided by a really big number, we can really just say that that really approaches 0. 1 divided by something really big is just 0. We're very close to 0 for our purposes. And that means when we divide by positive infinity, our value becomes 0 over 1. When we divide by negative infinity, it's still 0 over 1. So that's overall 0. So the value that the y approaches when x approaches positive or negative infinity is just 0. And that is our horizontal asymptote. So rational functions, let's go ahead and practice them now. So first we're going to talk about zeros and or vertical asymptotes, and that's one of the main characteristics. So if you have a linear function here and it's reciprocal, the linear function has an x-intercept or a 0. Here they're both drawn again for us. The 0 or x-intercept is at -2, so you can see that here. That same function, when we reciprocate it, the 0 becomes a vertical asymptote because it's a restriction, and there it is on our graph. We put a dashed line that's going through x is equal to -2. Horizontal asymptote, the linear function doesn't have any. The reciprocal function will have a horizontal asymptote at y is equal to 0, and there it is drawn right here. Intervals in which the graph is above the x-axis are positive intervals for the original function. That happens when x is greater than -2, and you can tell that's when the function is above the x-axis, the original or the blue one. The reciprocal function actually has the exact same characteristic. When x is greater than -2, the function is above the x-axis. Next characteristic is when the function is below the x-axis, and that just happens when x is less than -2 in the first case, and also x is equal to negative, or x is less than -2 for the reciprocal function. Intervals where the function is increasing or decreasing. So the linear function, the blue function, is always increasing. As we move from left to right, that's how we read the increasing or decreasing pattern. Going from left to right, the original is increasing. So it's always increasing. X is an element of real numbers, states that. The reciprocal function, well, that's actually always decreasing, right? It's always decreasing. The only place it's not decreasing is when x is equal to -2. So maybe we should put that because it actually doesn't exist there, right? There's a vertical asymptote, except at x is equal to -2, simply because it doesn't exist there. So it can't be decreasing or increasing. Okay, so finally, let's look at the algorithm for rational functions. So what you have to be able to do. So the steps that you should be able to follow when you're given a rational function. So you no longer have to be given a linear function. You can just be given the reciprocal of a linear, and you kind of have to figure everything out on your own. You can use what we just learned to determine it. So the first thing that you will have to determine is the x-intercepts. And from grade 9, you should remember that an x-intercept occurs when y, or f of x, is equal to 0. So if I set f of x is equal to 0 and I solve for x, I would make the function 0 is equal to 4 over x minus 6. In order to solve for x, I'll have to multiply both sides by x minus 6 because it's in the denominator, so I want to get rid of it. Now, on the right side, that'll cancel out. On the left side, I'm multiplying x minus 6 by 0. Well, that still stays 0. I end up with 0 is equal to 4. This here is never true. Something that's never true in mathematics really tells us that there is none. So x-intercept, there is none, because when we try and solve for it, we end up with something that's never true. So there's no x-intercept. The y-intercept in this case, again, you should know how to solve for it. The y-intercept, you solve it by setting x to 0. And in this case, when we set x to 0, we should end up with 4 over 0, take away 6. And that is really 4 over -6. And that really simplifies to -2 over 3. So that is our y-intercept. Y is equal to -2 over 3. To find the vertical asymptote, you have to set the denominator to 0 and solve for x. So if we do that in this case, we set the denominator to 0, which is x minus 6, and solve for x. It's quite easy to see that x is equal to 6. And that is our vertical asymptote. Horizontal asymptote, here's the first shortcut that we'll need for the unit. When the numerator is a constant, meaning just some number, doesn't matter what the number is, the rational function has a horizontal asymptote at y is equal to 0. So that's always the case. So that's awesome. We don't have to do that finding 5-step process. We can really just say y is equal to 0. And then we can go ahead and sketch. So based on everything that you just said, you should be able to sketch your horizontal and vertical asymptotes. There they are. You should be able to sketch the y-intercept. Again, we have it right here at -2/3. And the pattern of the function is always the same. It's got these two curves that approach asymptotes on both ends. The last thing that we'll talk about is the point of intersection. So you're asked to find the point of intersection between these two functions. And what does it really mean to find a point of intersection? Well, at the point of intersection, the two functions must be equal since they're intersecting. So we can just make them equal first and foremost. So 1 over x plus 2 will be equal to x plus 2, and then we solve for x using algebra. To solve for x, my first step would be to multiply both sides by x plus 2. That makes it easy. On the left side, x plus 2 will cancel out, so I'll end up with 1 is equal to x plus 2 squared. One way to now solve it is I can just take a square root on both sides to get rid of that exponent on the right side. And I'll end up with square root of 1, which is plus or minus 1, is equal to x plus 2. Don't forget the plus or minus 1. Oftentimes people will leave the plus or minus out, but when you take a square root of a number, the answer is either the positive or negative of that number. And then I can continue solving for x by throwing the -2 to the left side, or the +2 to the left side, and it'll become negative. So -2 plus 1 is equal to x is my first solution, or -2 minus 1 is equal to x is my second solution. The first solution, x will end up being -1. And from the second solution, x is equal to -3. So I've got two possible points of intersection. And in order to find the y values for these two x points of intersection, I can simply plug them into one or the other formula.